During primary drying, ice requires energy to sublime. But how does that energy actually reach the product? In a pharmaceutical freeze dryer, heat travels through several pathways before reaching the frozen formulation. Understanding these pathways is fundamental to controlling product temperature, sublimation rate, and ultimately the performance of the lyophilization cycle. In a typical shelf-based freeze dryer, the primary source of energy is the temperature-controlled shelf. Heat must travel from the shelf to the vial and then into the product. The efficiency of this transfer depends on the thermal properties and physical contact between each component of the pathway. The most direct heat transfer pathway is conduction. Heat moves through physical contact between materials, from the shelf to the vial, through the vial wall and bottom, and finally into the formulation. The efficiency of this pathway depends on factors such as vial geometry, material properties, contact area, and the thermal characteristics of the product. The contact between the vial and the shelf is particularly important. Even small differences in contact can influence the amount of heat transferred into individual vials. This can contribute to differences in product temperature and drying behavior across the batch. Heat transfer does not stop when the chamber is evacuated. Residual gas molecules can still transfer energy between surfaces. This mechanism is known as gas conduction. Its contribution depends strongly on chamber pressure and gas properties, meaning that chamber pressure influences not only mass transfer, but also the way heat reaches the product. A third pathway is thermal radiation. Surfaces within the freeze dryer can exchange energy through electromagnetic radiation without requiring direct physical contact. The contribution of radiation depends on the equipment configuration, surface temperatures, geometry, and radiative properties of the materials involved. Ultimately, the parameter we care about is not simply shelf temperature, but product temperature. During primary drying, product temperature reflects the balance between the heat being supplied to the product and the energy consumed by sublimation. This is why shelf temperature and product temperature should not be treated as interchangeable measurements. Consider what happens when the shelf temperature is increased. More energy can be transferred into the product, potentially increasing the sublimation rate. But if heat is supplied faster than the generated water vapor can be transported away, product temperature can rise. The process, therefore, requires a balance between heat input and vapor removal. Heat transfer during lyophilization is influenced by several variables, including shelf temperature, chamber pressure, vial geometry, vial-to-shelf contact, fill volume, formulation properties, and the thermal characteristics of the system. These variables interact, which is why changing one process parameter can influence the overall drying behavior. The heat transfer pathway can therefore be viewed as a chain. Energy is supplied by the shelf, transferred toward the vial through conduction, gas conduction, and radiation, and ultimately reaches the product, where it provides the energy required for sublimation. Understanding this pathway gives us the foundation for controlling product temperature and optimizing primary drying. But heat transfer is only half of the story. Once ice becomes water vapor, that vapor has to travel through the dried product and leave the vial. What controls that movement? Mass transfer. That's what we'll explore in the next episode.